All right, so let's talk about transient conduction. So, first question to ask is, when does this occur? Transient conduction occurs anytime that you're asking questions about time. So how long is it going to take for this to warm up? How long is it going to take for this to cool down? And you can imagine that might be important if you, say, removed some parts from a manufacturing process and you want to know when they're cool enough to handle or to manipulate. You might want to know when something is going to be solidified or a phase change is going to be complete. You might want to know, if you take the pie out of the oven, how long before you can eat the pie without burning your mouth. I tend not to wait long enough, and I tend to burn my mouth. But that's the way it is. So anything that's a question around time is going to be a transient conduction kind of question. So let's recall, let's actually think about a little example. So let's imagine that we have a tater tot, and the tater tot is sitting in some oil, and we're going to fry this tater tot. So this is a solid object being heated by some surroundings. So as a solid object, if we were interested in the temperature distribution inside, we would normally start with the heat diffusion equation, which looks like this. Okay, so here's the heat diffusion equation. Note that instead of writing 1 over alpha, I wrote what that actually is, which is rho c over k, so that's 1 over alpha. And in the past, we've always ignored this d temperature over time term, but now this is going to matter. Okay. Now, assuming that this object doesn't have any heat conduction on the inside, or any heat generation on the inside is what I should say, we can eliminate that q dot term. Now the question is, what would be the simplest case that we could possibly imagine? All right, and the simplest case that we could imagine would be an object that was isothermal. Okay, so instead of having temperature gradients, let's assume that that object doesn't have any temperature gradients and it's isothermal, no variation with x, y, and z. Now, I want to be real clear that it's not possible for this object, like this tater tot, for example, to be isothermal, because an object that's isothermal is going to have no temperature gradient. If it has no temperature gradient, it's going to have no heat transfer. If it has no heat transfer, it doesn't belong in this class. So in reality, every object where we're dealing with transient conduction is going to have some kind of temperature gradient. Okay, but it turns out that our analysis gets much simpler if we can ignore that temperature gradient. But let's look at the heat diffusion equation. If there's no temperature gradient, how is the heat diffusion equation going to change? We'll think about it for a second. What you should recognize is that if there's no temperature gradient, then all these derivatives are zero. And if all these derivatives are to zero, that's going to imply that the derivative of temperature with respect to time is also equal to zero. And that means that the temperature doesn't change. And if the temperature doesn't change, that can't be right. Okay, because the whole point is looking at how the temperature of an object is going to change over time. So what that means is that if we were to assume that an object is isothermal, then the heat diffusion equation doesn't work anymore, because we know if there's heat transfer, it can't be isothermal. And if there is heat transfer, it's not isothermal. And if it's not isothermal, then these derivatives stay. But if we get rid of them by assuming that the object is isothermal, then we have a problem. So what this is going to lead to is a different kind of approach, and that approach is called the lumped capacitance model. And in the lumped capacitance model, we're going to ignore the heat diffusion equation, because the heat diffusion equation doesn't work when you ignore the temperature derivatives. Okay, so lumped capacitance. What lumped capacitance is all about is that we're just going to do an energy balance instead of the heat diffusion equation. Because the heat diffusion equation is all about trying to understand what the temperature distribution is inside an object. But when we do lumped capacitance, we're going to assume that the object is isothermal. And if the object is isothermal, then obviously we're not caring about what the temperature distribution is inside the object, because we're saying that there isn't one, or at least not one that's significant enough to be thinking about. So then the question is, when can you assume this? When are you going to be able to assume that an object is isothermal? Okay, so when can this be assumed? Well, let's ask a question real quick. First of all, what impact do you think thermal conductivity K is going to have? Do you think an object with a high thermal conductivity is going to be more likely to be isothermal, or an object with low thermal conductivity? think about it for a second and just try and think physically, intuitively, what thermal conductivity is going to do. Is thermal conductivity going to make temperatures even out more, or is it going to lead to a larger temperature drop? So try and think about it. Do you think do you think an insulating object is going to be more isothermal or a conductive object? So keep thinking, keep thinking, keep thinking, keep thinking. Okay, hopefully you actually thought about it. If you thought about it, what you should have found is that high thermal conductivity is going to lead to an object being more isothermal. Okay? That high thermal conductivity makes it easier for energy to move. If it makes it easier for energy to move, then for a given amount of movement, you're not going to have as big of a temperature hill, right? So low thermal conductivity is going to give you a bigger hill to make the energy move. High thermal conductivity is going to give you a flatter hill to make the energy move. So what we really want to know with lump capacitance is what we want to know when we can assume that something is isothermal. And what we mean by isothermal is what we really want to know is how the temperature drop inside the object compares to the total temperature drop. Or to say it slightly differently, what we're trying to get down to is when the temperature variation inside the object is small compared to the total temperature change from hot to cold. When does most of the temperature drop occur outside of the object versus inside the object? And the way that we test that is we look at thermal resistances. And in particular, if you think about circuits, right? If you have electricity moving through a circuit and you have a little resistance and then you have a bigger resistance, where does the voltage drop occur? Well, the voltage drop is going to occur in the big resistance. Okay, so the main voltage drop is going to occur over the big resistor. This is like, you know, when you attach when you make a circuit and you attach a wire to a light bulb or to a resistor, the wire is actually a resistor too, but you ignore any voltage drop in the wire because the wire is such a small resistance compared to the resistor or compared to the light bulb. Okay, so we're going to look at the same kind of idea, except here we're going to use thermal resistances. So the real question that we have is if, you know, let's say this is our tater tot, which is at some temperature, we'll call it Tc, and then the surface of the tater tot is at some temperature Ts, and then the oil is at some temperature T infinity. The question is, how does delta T inside the object, in this case a tater tot, compare to delta T outside the object? Okay, and if you think back to just basic thermal resistances and thermal resistance analogy, delta T equals QR. So delta T inside is going to be Q times R interior, for the interior of the object, and the delta T outside the object is going to be Q times R on the outside of the object. And it's the same heat transfer that goes through both, so Q is going to cancel. Okay, and in this case, the interior is going to be conduction, which is L over Ka. The exterior is going to be convection, which is 1 over HA. Assuming that the areas are roughly the same, which is what we're going to assume here, that means that this ratio is equal to HL over K. And this ratio is what we call the Biot number. And this is going to be the big predictor of whether or not we can assume lumped capacitance. Okay, so the Biot number. What we're going to check is we're going to check if the Biot number is less than 0.1. If so, we can do lumped capacitance. If not, then our life gets more complicated. And we'll pick that up in the next lecture, is what we do when we can't assume lumped capacitance. All right, so we've talked a lot about this idea of lumped capacitance and whether this object is isothermal, and the Biot number is our test to determine whether it's isothermal. But I haven't actually talked about how we do lumped capacitance, so let's talk about that. And actually, before I get into what lumped capacitance is, let me talk a little bit more about the Biot number. A couple of notes. First note, is that, remember that we're comparing the interior resistance to the exterior resistance. And in this case, Biot number assumed convection on the outside. But keep in mind that we can make this same internal versus external resistance comparison. This would apply for any external environment. Okay, so this would apply for an object buried in a solid. It would apply for radiation on the outside. The HL over K is only one specific situation. It happens to be the one that's the most relevant and the one that's the most important. But keep in mind that I could, for example, on an exam, ask you to tell me what would be the criteria to test if you had radiation, or what would be the criteria to test if you had an object that was buried in a solid rather than surrounded by convection. Okay? So that's the first note I want to make. The second note I want to make is that not all objects are conveniently shaped with a well-defined length L. For example, they could be some arbitrary shape. And so what we use instead of L we use a characteristic length LC, where LC is defined as the volume over the surface area. Okay, so when we're testing whether or not we can use lump capacitance, we check the Biot number. If the Biot number is less than 0.1, then we can. If it's not, then we can't. But when we do that test, we have to use a characteristic length, which is volume over surface area, and that allows us to handle shapes of arbitrary geometries. Okay. The other thing I want to mention as well is that, let's say you calculated the Biot number and it was 0.100001, and the question is, well, is that less than 0.1? Who knows? Well, clearly it's not, but is it close enough? And that's where heat transfer, again, comes into this question of what's close enough. How accurate do you need your answer to be? When you're calculating the Biot number and you're deciding whether or not lump capacitance is appropriate, 0.1 is a rule of thumb. It's a rough guideline, but the real question is how much accuracy do you need, and that's going to affect whether or not you can treat it as a lump capacitance model. Okay, so again, we've talked about the test to determine whether or not you can do lump capacitance. Let's talk about what lump capacitance is. Okay, so when we do lumped capacitance, what we need to test is we need to test whether the Biot number is above 0.1 or less than 0.1. But then what we do, remember I said that the heat diffusion equation doesn't apply for lump capacitance. And the reason it doesn't apply is that lump capacitance says the object is isothermal and it ignores the temperature gradients. And that doesn't work because the temperature gradients are necessary to drive the heat transfer. But if we can say that the temperature change inside the object is small, then we don't really care about what's going on inside the object and we ignore the heat diffusion equation. Instead, what we'll do is an energy balance. And so a basic energy balance says that energy in minus energy out equals energy stored. Instead of looking at total energy, let's look at rate. So the rate at which energy comes in minus the rate at which energy goes out is going to be equal to the rate at which energy is stored inside an object. Okay. Now, if you remember from basic thermodynamics of solids, the energy stored in an object is going to be the mass times the specific heat times the change in temperature. So if you're looking at the rate of energy change, then you need the rate of temperature change. So that's going to be mass times specific heat times the rate at which the temperature changes. Okay, when we can rewrite the mass as density times volume. And if we go back again to our tater tot analogy, where we have a tater tot surrounded by oil, okay, the rate at which energy flows in, remember the oil is going to be hot, tater tot is going to be cold, the rate at which energy flows in is going to be convection, which is going to be H times the surface area times T infinity minus Ts. And the reason it's T infinity minus Ts is here we're assuming that energy is flowing in, and if energy is flowing in, then T infinity is going to be bigger than the temperature of the tater tot, and there's going to be no energy flowing out. Okay, so now we're going to do something very similar to what we did for fins, and we're going to define a variable theta, which is equal to T minus T infinity, and we're going to note that d theta and dt are the same thing. Okay, If you don't remember the mathematics on this, just think back to fins and go back through your notes there. It's the exact same analysis, exact same approach. And then that means that we can rewrite this equation, this energy balance equation up here. It's now going to be HA theta equals rho v c d theta d time. Now with a little bit of rearranging, that means that, this is negative HAS theta. With a little bit of rearranging, we can make that say that negative dt equals rho vc over HA times d theta over theta. Now we can integrate both sides. If we integrate both sides, with integrals we have two choices. We can either do a general integral or an unbounded integral. That's when you get the constant of integration. Or you can have a bounded integral, and then you don't get a constant of integration because the integral is going between two very specific places. So let's take our integral from time 0 to some arbitrary time t. Okay? And let's assume that at time 0, the temperature of the object is some initial temperature Ti. And that means that theta, which is T minus T infinity, is going to be Ti minus T infinity when it's theta I, which is the theta at time 0. So that means the bounds of integration for theta are going to be theta I all the way to some temperature theta at some time t. Now, if we do this integral, we get a minus t on the left side, and we get rho vc over HA times the natural log of, hold on, let me scroll down. Sorry, natural log of theta over theta I on the right side, which when you take care of the exponential, this is going to become theta over theta I equals e to the HA over rho VC T negative. Okay, so this is a negative exponential. Recall theta, that's basically temperature as a function of time. Theta I is the initial temperature. And what this says is that the ratio of the temperature over the initial temperature, or I should say the temperature difference between the object and the ambient, and the initial temperature difference goes as a negative exponential, which means that gradually over time, theta is going to approach 0, okay? And it's going to asymptotically approach it. And it should make some sense that it's going to be an asymptotic approach, because as the object gets closer to the ambient temperature, or initially it's going to be far from the ambient, you're going to get a lot of heat transfer. But as it gets closer and closer to the ambient, the temperature change, or the temperature difference gets smaller and smaller. As that temperature difference gets smaller, the heat transfer gets smaller. As the heat transfer gets smaller, the rate at which the temperature changes is going to get slower. Okay, so negative exponentials look like this with an asymptotic approach. Okay, and so initially you're at theta I. So here's theta as a function of time. Initially you're at theta I, and gradually theta is going to approach 0 as the temperature of the object approaches the ambient. Okay, and you're going to get that asymptotic approach.
Yeah, that's okay.
Okay. Okay, so let's talk about negative exponentials for a bit. First thing, something that you do a lot of times, especially if you have a negative exponential with time, is you define a time constant, tau. And tau is equal to 1 over all the stuff that's multiplied by time. So in this case, tau is going to be equal to 1 over HA times rho VC. What you should recognize is that this is a resistance term, and this is a capacitance term. So this is actually the same mathematics as you get when you have an RC circuit in electronics. Okay? But the main thing that I want you to notice here is that tau gives you an idea of what the time scale is over which things change. For example, for negative exponentials, when time equals 1 tau, you get e to the negative 1, and that's going to take you 63% of the way along the decay curve. When time is equal to 2 tau, sorry, I need to scroll again. Okay, when time is equal to 2 tau, that's when you go 86% of the way along the decay curve. And when time is equal to 3 tau, that's when you go 95%. So, kind of gives you an idea of what the time scale is. When time is equal to 3 times a time constant, you know that you've gone 95% of the way along the decay curve, which in this case means that the temperature of the object is 95% of the way to the temperature of the ambient environment. Okay, so that gives us temperature as a function of time, and it talks about some of the time dependence of temperature and the fact that it exponentially decays towards the ambient temperature. But we also might want to know the total amount of heat transferred. Okay? And there are two kind of different ways that you could think about calculating the total amount of heat transfer. And as it turns out, they both give the exact same expression, which is kind of convenient. The first way is to use the fact that this is a lumped model. And so capital Q, the total amount of energy transferred, is just going to be equal to the thermodynamic amount of energy associated with changing the temperature of a solid object, which is the mass, which is the density times volume, times specific heat, times change in temperature. Okay. And substituting, that's rho VC times the difference between the initial temperature and the final temperature. Okay, so that's going to be the total heat transfer. Notice I use thetas. Since theta is T minus T infinity, then theta I minus theta is the same as Ti minus T. Okay? So, that's one way we can express it. The other way we can do it is we can think of Q, the total amount of energy transferred, as being an integral of the rate at which heat is transferred over time. So, substituting, that's going to be the integral of HA theta times d time, because the rate of heat transfer is the convection, HA theta. So HA is going to pull out of the integral. We're going to integrate this from 0 to some time t, and that'll give us the amount of heat transferred over that time. And if you do the substitution for theta, what you eventually are going to get to is that Q equals rho VC theta I times 1 minus e to the negative t over tau. Okay, that's just the basic integral of an exponential, which I'm trusting that you're able to do. If you want to go and drive it for yourself, you are more than welcome to. But this equation and this equation turn out to be the exact same thing, which is kind of good to know. Okay, so just to recap. When we talk about transient heat transfer, that's what we're talking about when we're asking how long something is going to take, the time required for something to heat up or to cool down, which is a question that shows up quite a bit in heat transfer. And then in terms of how we analyze it, there's sort of two general approaches. One is the simplified version, which is lumped capacitance. The other one we'll get to in the next lecture, which actually requires the heat diffusion equation. In lumped capacitance, we assume that the temperature of the object is pretty much uniform. It can't truly be uniform, because if it were uniform, there'd be no heat transfer, but we assume that it's close enough. And the key with assuming that it's close enough is we're assuming that the temperature variation inside the object is much less than the total temperature drop from the object to the ambient. Okay? And the test for that is the Biot number. So we calculate the Biot number. If it's less than about 0.1, then we say it's good enough and we do lump capacitance. If it's not less than 0.1, then we say it's not good enough and we do this other approach that we'll get to next time. We found that when we did the lump capacitance approach, we did an energy balance, we integrated it, we ended up with a negative exponential, which says that the temperature of the object decays in an exponential way towards the temperature of the ambient. We talked about the time constant, which gives you an idea of what the time scale is of that decay. And then we also derived some expressions for the total amount of energy transferred. So that is where we're going to leave it for now, and we'll pick this up with the more exact solution, which is more complicated, next time.